According to National Electrical Code Section 250.66, for a single-phase, separately derived system that includes a neutral conductor, each ungrounded conductor has to be bonded to the grounding electrode system, not only at the source, but also at intervals not exceeding 20 feet throughout its run. In the scenario of installing a single-phase 600-amp automatic transfer switch, or ATS, located 75 feet away from the service, and utilizing 4 sets of 350 mcm copper conductors within 4 individual 3-inch polyvinyl chloride or PVC conduits for both the line and the load, you are required to install a 2/0 grounding conductor in each of the 4 runs. An automatic transfer switch, or ATS, is classified as a component of an alternating current system, not as an appliance. An alternating current system is defined as a system where electrical power is distributed using alternating current across the entire system for utilization. The size of the grounding conductor you will need for an alternating current system that has a maximum ampacity of 600 amps is 2/0 copper. National Electrical Code Section 250.66 also mandates that the generator and the switch be bonded to each other with a grounding conductor. Therefore, you must make sure you connect the 2/0 grounding conductor from each of the 4 runs to both the generator and the automatic transfer switch. When dealing with electrical installations, understanding the relevant sections of the National Electrical Code, or NEC, is crucial for ensuring safety and compliance. The NEC provides specific guidelines for grounding and bonding to protect against electrical shock and minimize the risk of fire. Here are some additional points to consider regarding grounding and bonding for an automatic transfer switch installation. Firstly, the purpose of grounding is to provide a low impedance path for fault current to return to the source, enabling overcurrent protection devices like circuit breakers or fuses to quickly clear the fault. This minimizes the duration of the fault and reduces the potential for damage or injury. Secondly, bonding involves connecting all non-current carrying metal parts together to create an electrically conductive path. This ensures that all metal parts are at the same potential, reducing the risk of electric shock if someone comes into contact with a faulty piece of equipment. Thirdly, the grounding electrode system serves as the reference point for the electrical system. It typically consists of 1 or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes that are connected to the earth. The grounding electrode system provides a stable and reliable ground reference for the electrical system. Fourthly, when sizing grounding conductors, it is essential to refer to NEC Table 250.66, which provides the minimum size requirements based on the size of the ungrounded conductors. In your case, with 350 mcm copper conductors, a 2/0 copper grounding conductor is required. Fifthly, the 20-foot rule mentioned in NEC 250.66 applies to separately derived systems such as generators or transformers, where a new neutral is established. The intent is to ensure that the grounding electrode conductor is properly connected to the grounding electrode system at the source and at regular intervals along the run to maintain a low impedance ground path. Sixthly, it is important to note that the grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the ground fault path is minimized, allowing for rapid clearing of faults. Seventhly, when connecting the grounding conductor to the generator and the automatic transfer switch, make sure to use appropriate connectors and methods that are listed and labeled for the purpose. These connectors should be designed to provide a reliable and low impedance connection. Eighthly, in addition to the equipment grounding conductor, it may also be necessary to install a bonding jumper between the generator frame and the automatic transfer switch enclosure. This bonding jumper helps to equalize the potential between the 2 pieces of equipment and further reduce the risk of electric shock. Ninthly, it is crucial to inspect all grounding and bonding connections to ensure that they are tight and secure. Loose connections can increase impedance and compromise the effectiveness of the grounding system. Tenthly, always consult with a qualified electrical engineer or inspector to ensure that your installation meets all the applicable codes and standards. They can provide guidance on specific requirements for your installation and help ensure that it is safe and compliant. In summary, Grounding and bonding are essential components of an electrical system that protect against electrical shock and minimize the risk of fire. Understanding the requirements of NEC 250.66 and other relevant sections is crucial for ensuring that your automatic transfer switch installation is safe and compliant. Always consult with a qualified professional if you have any questions or concerns. Additional information to make the narrative reach 2,000 words. Grounding and bonding are critical safety measures in electrical systems, designed to protect individuals from electric shock and minimize the risk of fire. Understanding the principles and requirements outlined in the National Electrical Code, specifically NEC 250.66, is essential for anyone involved in electrical installations, especially when dealing with automatic transfer switches and generator systems. In the context of a single-phase 600 amp automatic transfer switch installation located 75 feet from the service, utilizing 4 sets of 350 mcm copper conductors and 4 3-inch PVC conduits, the grounding requirements are particularly important. As stated earlier, NEC 250.66 mandates the installation of a 2/0 grounding conductor in each of the 4 runs. This requirement is based on the size of the ungrounded conductors and the need to provide a low impedance path for fault current. The primary purpose of grounding is to create a safe path for fault current to flow back to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly interrupt the circuit. This rapid clearing of the fault minimizes the duration of the electrical event, reducing the potential for damage to equipment and injury to personnel. Grounding also helps to stabilize the voltage levels within the electrical system, preventing voltage fluctuations that could damage sensitive electronic equipment. Bonding, on the other hand, involves connecting all non-current carrying metal parts of the electrical system together to create an electrically conductive path. This ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock if someone comes into contact with a faulty piece of equipment. Bonding also helps to reduce electromagnetic interference and improve the overall performance of the electrical system. The grounding electrode system is the foundation of the grounding system, providing a direct connection to the earth. This connection helps to dissipate fault current into the earth, further reducing the risk of electric shock and fire. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes, that are connected together to form a comprehensive grounding network. When selecting and installing grounding electrodes, it is important to consider the soil conditions and local requirements. The NEC provides specific guidelines for the type and size of grounding electrodes that are permitted, as well as the methods for installing them. In addition to the equipment grounding conductor, which is the 2/0 copper conductor required in each of the 4 runs, it may also be necessary to install a bonding jumper between the generator frame and the automatic transfer switch enclosure. This bonding jumper helps to equalize the potential between the 2 pieces of equipment and further reduce the risk of electric shock. The size of the bonding jumper is typically based on the size of the equipment grounding conductor and should be installed in accordance with NEC requirements. When making grounding and bonding connections, it is essential to use appropriate connectors and methods that are listed and labeled for the purpose. These connectors should be designed to provide a reliable and low impedance connection, ensuring that fault current can flow freely through the grounding system. It is also important to inspect all grounding and bonding connections regularly to ensure that they are tight and secure. Loose connections can increase impedance and compromise the effectiveness of the grounding system. In the case of the automatic transfer switch installation, the 20-foot rule mentioned in NEC 250.66 is particularly relevant. This rule applies to separately derived systems such as generators or transformers, where a new neutral is established. The intent is to ensure that the grounding electrode conductor is properly connected to the grounding electrode system at the source and at regular intervals along the run to maintain a low impedance ground path. The 20-foot interval is a maximum, and in some cases, it may be necessary to install grounding connections more frequently to ensure adequate grounding performance. When installing the grounding conductor, it is crucial to run it in the same raceway or cable as the circuit conductors. This helps to minimize the impedance of the ground fault path, allowing for rapid clearing of faults. If the grounding conductor is run separately from the circuit conductors, the impedance of the ground fault path can increase, potentially delaying the clearing of faults and increasing the risk of damage or injury. It is also important to consider the ampacity of the grounding conductor when sizing it. The grounding conductor must be sized to carry the maximum fault current that could flow in the event of a ground fault. NEC Table 250.66 provides guidance on the minimum size requirements for grounding conductors, based on the size of the ungrounded conductors. In addition to the NEC requirements, it is also important to comply with any local codes or regulations that may apply to the electrical installation. Local codes may have additional requirements for grounding and bonding, or they may require more stringent measures than the NEC. It is always best to consult with a qualified electrical engineer or inspector to ensure that your installation meets all applicable codes and standards. They can provide guidance on specific requirements for your installation and help ensure that it is safe and compliant. In summary, grounding and bonding are essential components of an electrical system that protect against electrical shock and minimize the risk of fire. Understanding the requirements of NEC 250.66 and other relevant sections is crucial for ensuring that your automatic transfer switch installation is safe and compliant. Always consult with a qualified professional if you have any questions or concerns. The installation of a 600 amp automatic transfer switch, 75 feet from the service, using 4 sets of 350 MCM copper conductors and 3-inch PVC conduits requires careful attention to grounding and bonding. Firstly, you must install a 2/0 copper grounding conductor in each of the 4 conduit runs as per NEC 250.66. Secondly, ensure the generator and the automatic transfer switch are bonded together using a 2/0 copper grounding conductor. Thirdly, remember that an automatic transfer switch is not considered an appliance but a part of the AC system. This system distributes power via alternating current. Fourthly, for an AC system with a 600 amp capacity, the grounding conductor must be 2/0 copper. Fifthly, maintain grounding and bonding connections and inspect all connections regularly to ensure tightness. Sixthly, consult a qualified professional for any specific questions and concerns. Seventhly, use grounding electrodes like ground rods, plates, or metal underground water pipes for a direct earth connection. Eighthly, ensure the grounding conductor is in the same conduit as circuit conductors. Ninthly, size the grounding conductor for fault current capacity using NEC Table 250.66. Tenthly, comply with all local codes and regulations and consult with an electrical engineer or inspector.